Hello everyone, my name is Ambre and today I'm going to present you our paper handling non-visible reference in situated visualizations in collaborations with INRIA's researchers Arnaud Prouzeau, Martin Hachet and Pierre Dragicevic. So situated visualizations are a type of visualization, here vitals about a fire victim, where data is presented next to its physical referent, meaning the physical object, space or person it refers to. While situated visualizations can be beneficial in various contexts and have received research attention, they are typically designed with the assumption that the physical referent is visible. When performing a task with situated visualization, like here, where a firefighter has to save a victim, the physical referent may be occluded by another object, such a wall. In our paper, we provide an overview of techniques proposed in the past for dealing with non-visible objects in the areas of 3D user interface, 3D visualization, and mixed reality. We then derive a design space that applies to situated visualizations to examine various trade-offs, challenges, and opportunities for future research in this area. We mainly envision that our conceptual framework will be most useful in the hands of designers of new situated visualizations to help them support non-visible reference. In this presentation, I'll start by describing the wide range of situations in which an object is non-visible. I will illustrate components of our conceptual framework, and I'll end up by presenting a use case. In the real world, there is a wide range of situations in which the physical referent may be non-visible. An object is out of view if it is not within the user's visual field but can be seen if the observer turns their head. An object is occluded if it's in sight but is blocked by another object. We more specifically refer to an object as hidden if it is in the user's vicinity but occluded from all reachable locations and viewpoints. An object is illegible if none of its useful details is visible to the user for reasons other than being out of view or occluded. I'll now move on with our conceptual framework components. So, we gathered 107 papers through keyword searches on several scientific search engines and added papers cited in the 2008 Taxonomy of 3D Occlusion Management techniques from Elmquist and Sigas. In order to keep the size and complexity of the survey and of the resulting design space within reasonable limits, we iterated over a set of criteria to restrict the scope of our survey. We divided these works into 8 families of XR techniques that could deal with the non-visibility of objects of interest. Here are 2 examples of families of techniques. One of them is X-ray vision. X-ray vision techniques emulate the fictional superhuman ability to see through occluding surfaces. Here, a user can see heat data even if the physical referent is occluded by walls. Another one of them is virtual twin. A virtual twin is a dynamic 3D model that conveys the visual appearance as well as the key properties of a physical system of objects, such as its states, features, physical measurements, and so on. Here, the user can perform an analytical task on the object of interest even if it's illegible because located in another location. I'll now move on with our design space dimensions. So we came up with 14 design dimensions and split them into 3 categories. The first one is a general category. The second one refers to the representation. The third one is about visualization. First, the general category. So the non-visibility support refers to the types of non-visible physical reference that are supported. Interactivity refers to the extent to which the user can interact with the representation or visualization. The interaction realism refers to the extent to which the interaction techniques are reality-based. And actionability refers to the extent to which the user can act on the non-visible physical reference. For a low value, the situated visualization system does not let the user act on the physical reference. For a medium value, the technique supports basic action on the physical referent, such as flipping electronic states on and off. For a high value, the technique allows rich manipulations on the physical reference. Now, the representation category. Representation fidelity refers to the level of detail with which the physical referent is represented. The representation refresh rate refers to how often the representation of the referent is updated to reflect the real referent. The surrounding inclusions refers to how much the environment around the referent is included in the representation. The representation medium refers to whether the representation of the physical referent is digital or physical. And the representation integration refers to what extent the representation appears to be integrated in the user's environment. So if the representation is physical, its integration with the physical world is necessarily high. If it is digital, it depends on the visual metaphors and rendering techniques used to display it. For a low value, the representation of the referent does not appear integrated in the physical environment at all, and it is very clear that this representation is a virtual image. For a medium value, there is some sense that the representation is integrated in the physical environment, but its integration is not fully believable, like here, where occlusion is not handled. For a high value, the representation appears to be an integral part of the physical environment. So for the three ones that are above, they are very similar to the representations one, so I'm not going to go through it anymore. But there's a very particular one in this category, which is visualization richness, which refers to the amount of data visualized about the physical referent. For a low value, the situated visualization system shows minimal information, such as the name or the location of the physical referent. For a medium value, the system visualizes some data about the physical referent. For a high value, the system visualizes a lot of data about the physical reference, allowing the user to perform an analytical task. Now I'm going to pursue with a use case. Some buildings, like factories or power plants, contain many sensors producing large quantities of data. Technicians need to understand this data to be able to deal with failures and optimize the building behaviors, like for energy consumption. It can be useful to have AR systems that can position data visualization directly near their physical reference, but often the physical references are non-visible. Consider, for instance, an air conditioning system. Objects of interest may include air handling units, air return fans, dampers, pipes, and vents. Most of these are non-visible due to occlusion. They are either behind walls or in the ceiling or in the floor. Suppose we want to have the technician diagnose air conditioning problems from anywhere in the building. The AR system could use a virtual twin to provide as much as useful information as possible about objects of interest. Suppose we want to help them locate and fix the problems when they are in the room. In this case, choosing a technique with high integration, like X-ray vision, seems very well suited, as technicians may need to quickly test and fix broken equipment. While equipment repair often requires physical presence, other building maintenance tasks can be done through the remote control of electrical and mechanical equipment. In these cases, integrating remote control features directly in the situated visualization system itself can help support actionability. So I'll now go through a conclusion. So first, sure, our design space have some limits. For instance, it would sure benefit from validation of the framework's generative power. For example, by asking designer to prototype situated visualizations with and without our framework. Secondly, of course, our design space does not cover all possible designs, for instance, due to our set of requirements of including a technique or not. As a summary, this framework consists of a terminology, a typology of techniques, and a design space. Our framework reflects the diversity of mixed reality techniques that can be used to address a variety of situations in which physical references are non-visible. It also highlights areas that remain unexplored and opportunity for future research. Thank you very much for your attention.